Good morning.
We'll just see the science of
Ah.
the
Well, thank you very much for inviting me. This was an interesting question for me. It made me feel that I am getting older. I am older, but when you get to this kind of philosophical talk, you know that you've been around for a while and somebody wants some philosophy from you, because really that's what this is going to be about. I actually feel quite passionately about what the question is. I think these two really are symbiotic, but you'll see I have some unfortunate cynical views of this as well. But my own career has been exactly this. It's been an interaction back and forth between research and practice, and it's been wonderful for me. So I would never change it. So just some jargon issues to begin with, because when I was tackling this and I began to think about it, some of the definitions become important. So words like researcher or medical scientist, are they the same? Like, what are they? Clinician versus clinician scientist, non-academic versus academic. I'm not going to define these, but just keep these subtleties in mind as we go on. And the whole science issue is becoming a bigger problem, because medical schools are de-emphasizing science curriculums. I know in my own institution it's been dramatically reduced. And from the basic science people, there's a major concern are whether our students are actually getting the fundamentals. I don't think they are. So actually, when I trained in Toronto many long years ago, there was this really classic town versus gown conflict. So for those who English as a second language, the idea is the academic was the gown and the town person was the clinician who was not a researcher. So the clinicians were viewed as with strong clinical skills, great diagnosticians, but knew little science. And the scientists that, well, they don't really know any science, but they were revered as great clinicians. So a little clinician, or something a little lighter, what fits your busy schedule better, exercising 1 hour a day or being dead 24 hours a day. And the scientist had the great scientific knowledge, but our view as residents was this person is best not left with patients. It's not safe. And this one here, the Center for scratching their heads. So clinician scientists, what they do though, and why I think it's so important, they bring a critical eye to the bedside. So in most of the 20th century, there was not much distinction between clinicians and clinical scientists. Consider, for example, my own institution where I was educated at the University of Toronto, Banting and Best in the discovery of insulin. This was a surgeon who went off into the lab, had an idea, started playing with this, and comes up with insulin. Or one I'm going to give you now is the example of mistents and cystic fibrosis. So when I grew up, the Cystic Fibrosis Society's campaign was based on having these tents for all children with cystic fibrosis to provide them with better oxygen and humidification. And one of my great fears as a 6 or 7-year-old was seeing these, oh, please, I never want to be in one of those tents. They were so scary. So then the question came up, do they actually work? And then it was said to be, is it ethical to test the role of these mistents in cystic fibrosis? So this paper was finally published in Pediatrics in 1972. And in this example, the physician understood the physics of gases and realized that carbon dioxide is heavier than oxygen, so it would settle to the bottom of the tent, displace oxygen, and actually make the kids worse. But then people thought, you can't do that study. It's unethical. Plus, it was the poster for the Cystic Fibrosis Society's campaign for getting money. Well, here was the study, and what he finds is that, in fact, it did make the Vmax, it was worse, basically, when you did this, for the very reason that he said. So this was a clinician, understood the basics of the science, goes ahead and does a trial and makes an extremely important adaptation. So it was not a long process like you have to go through today, but you also can't do these as easily today. Now I just want to switch a bit to how do we actually think as doctors? And I had the privilege of working with this woman, Vimla Patel, who did a lot of work in this area, and I was helping her with some of her models. And she's a cognitive scientist. So you have two domains of knowledge. You have many domains in your head, but for us, you have two primary ones as clinicians. You have a basic science domain, and you have a clinical domain. And these are separate parts of your brain and separate sets of knowledge and facts. This becomes very important for medical education. It becomes very important in how you think, and very important for this subject is, do you need science or not? So the domains are collections of facts and experiences. So knowledge levels and scientific reasoning. Well, if we're using, one of the examples we used was cardiovascular reasoning being my expertise. So first are definitions. Cardiac output is heart rate times stroke volume. Preload is, afterload is, simple definitions. The second level is conceptual. The determination of cardiac function is preload, afterload, contractility, and heart rate, these terms that you've already defined at the previous level. And the third level is the one that's really important, is complex concepts. So now you have definitions, you have put them together as cardiac function, and then you, oops, sorry, too fast. Then you now put them all together to see how they work. So now to really use these things well, you require expert reasoning, which means building up experiences in the domain of the expertise. So now we have two domains. If you want to be a clinician scientist, you have a science domain you have to work on and a clinical domain. They are separate. As physicians, we really should have both. I'm going to show you, I don't think we actually often do. And a classic example of an expert would be where the studies have been done is a chess player. And they know they need like 1,000 hours in repetitive activity to really be the master chess player. So an important part of the way an expert thinks is called adductive reasoning, ADD. It's a form of logical reasoning that goes from observations to a theory which accounts for the observation, and ideally seeking the simplest and most likely explanation. It's an inference to the best conclusion. First brought up by this guy Charles Sanders Peirce in the last, actually 2 centuries ago. So unlike deductive reasoning, the premise does not guarantee the conclusion. It requires building up experiences. I'll give you a simple example. The grass is wet, and you conclude it rained last night, because that's been your experience, and that's usually the answer. Although it actually could be that the sprinkler was on, or both. But if you know the weather, and if you, this is unusual weather, I think, in Europe at this time of year. I was just in Amsterdam. It was sunny the whole time. Unusual. Most of the time, if you took the first, you're going to be right. And it's a faster way of thinking, and as clinicians, it's a big part of what we do. You do want to qualify it, though, and come back and make sure that something else isn't happening. So it's the simplest and most likely explanation. It's fast, you know what's going on, and it lets you move quickly. And that's both clinically, and even the scientist sees something and jumps to a conclusion. An important part of the thinking is what's called forward and backward reasoning. So one of the studies I did with Imla was we gave questions to experts and novices. And we used a simple thing to start with. Person has retrosternal chest pain going down the left arm brought on by exertion. So even first-year medical students think ischemic heart disease. But then, so that's the forward and the easy part, the association. But then we go, and it goes straight through to the back. And anybody with clinical skills goes, whoa, that doesn't quite fit. Or it is worse when taking a deep breath. So now you begin to modify what you had. You had that initial adductive part, fast, great. Something doesn't fit, and you go back and modify. So this requires building up a lot of skills, having things really solid in your brain so you can move back and forth with them. So now if you've built up a solid science domain and a clinical domain, they can work together. And now they can begin to interact back and forth. But you have to develop these, and they take time to develop, but once you have, they can help each other. Now, Karl Popper is a well-known person in reasoning, and he rejected classical views on straight inductivist, A implies B implies C reasoning, and favored a method of empiric falsification. So a theory is an empiric sciences can never actually be proven. It can be falsified. So we're going to hear about hypotheses on the next talk. He's probably going to change the slide after this one. Maybe not. But so that's what you do in science. You have a hypothesis and you try to disprove it. you actually should be doing that clinically. You come up with an adductive thought, you have a hypothesis, and then you're testing it constantly. Do the other things fit? Is it okay? But you've really made your conclusion in the first 10, 15 seconds. I come from a cardiology background. I think the reason why I do critical care is the cardiology was like in the first 10 seconds, you know the answer, and if you don't know the answer in the first 10 seconds, you're not going to know it for a week. So it's something very different. So science may be described as part of a systematic oversimplification, actually. Now, I like this quote, though. Whenever a theory appears to you as the only possible one, take this as a sign that you have neither understood the theory nor the problem which it is intended to solve. And I think this should be a motto for all clinical scientists and actually for clinicians too, because we are always hypothesis testing at the bedside. So do clinicians actually need scientific knowledge? Well, I love my science part of my career. It's been a really important part to me, but I actually feel that most medical practice is actually at a brain stem level. I did this last time and he died. I won't do it again. I did this last time and he got better. I will do it again. So what's interesting is even using wrong scientific models can be a useful memory tool. Here's one example. So here's a classic Starling curve with a plateau. And then there's the thought that, is there a downward part to a Starling curve? And this has been argued a lot. What really is happening is that the whole function curve goes down. So it looks like there's a downward part to the curve. So if you think there is one, it can actually be useful clinically, because if you give too much fluid, you will get that effect. But that's not actually what happened. The whole curve changed. But the consequence for you is the same. So even having the wrong theory, you were okay. And it helps you remember, oh, I can't give too much, it'll make them worse. So back to this brainstem point. The reason why this is important, hypothetical deductive reasoning is just far too slow. You can't do, okay, so he has this, so it could be that, so it could be that, could be that. And especially in the ICU, he's dead by the time you do your A, B, C, D. You have to have responses. It becomes really important in things like anesthesia over short times. The reflex has to be there. You have to be able to modify it. You have to know, whoa, something's different. But most of the time, if you stop and start thinking, you're actually going to be in trouble. So the implication of this is that we learn by experience, and the more the experience, the better. So on the clinical side, on call, it sounds like propaganda to juniors, but I think it really is important. You have to get that time at the bedside where you actually make those decisions, get the experience, and go through the consequences. In our educations and the education system of controlling the time of residence and the work times, I think it's disastrous to become experts and getting what we need to have that skill. So it's also essential, as I said, for scientific reasoning, and is obtained by doing studies, reviewing studies, and following current advances. It takes work. You can't just dabble at this. And that's where the problem really comes in. It is a lot of work. So how do you maintain expertise? And especially today, as things really are advancing at a rapid rate. So basic science in the ICU clinician. Whereas 95% of practice, as I said, I think is at a brainstem level, we are frequently exposed to that 5% that requires new reasoning and scientific knowledge. Doesn't happen that often, but it does occur. If you're managing somebody on an ECMO circuit, you have to have some idea of how the system works, or you can get into real trouble. Now, if you've done it a lot, you'll eventually learn all the problems, and then you don't really have to know the science, but in between, there's a lot of people that might have taken a hit. And it gives a deeper understanding of how things work. It helps you understand physiological limits. And just think of it. Why does a football player, I had to put that in for here, or a hockey player in my country, work out in a gym rather than just play games? Because you have to strengthen and work out all parts the same way. For us as clinicians, it helps if you exercise other parts of your brain that are going to potentially help you in those crises. So what type of research for the clinicians? So when I started thinking about this talk, there's many different types we could think of. So in vitro, which would be cell culture, genetics, biochemistry, could be whole organ, which is systems biology, animals, humans, applied physiology, or clinical investigation, which of course is research as well, observational, clinical trials, outcomes, quality assurance. So the basic research gives insight into how the body works, teaches a quantitative component of what's possible. So we also have to think about research during training and research when you've finished, and I think they have different roles. The research during training teaches you how hard it is to obtain even garbage. You do your study and like, oh, man, this is terrible, but man, it was a lot of work to get that stuff, and become much more sympathetic to what you read. You also learn how easy it is to convert noise into a message. So some of the things you want to learn is checking for errors in data collection, choosing appropriate statistical techniques, and you're going to hear about all these today, and how you exclude some subjects based on predefined criteria. So sometimes you want to do this, so it's not just noise, but you got to be careful that you're not biasing things. And you want to make sure that you don't overstate your results, only exclude based on consistent and well-defined principles. Having done a study, you'll watch for this in other people's research and have a better idea, and it'll teach you also a healthy skepticism. So on the one side is teaching you, man, it's really hard even to get that lousy stuff, but on the other part is, hey, I had some of that, I knew how I put it together, and I'm not quite sure I'm going to actually believe that. So I think those are two really important parts, the skepticism as well as at the same time, actually, little respect for the work that went into it. And it helps you evaluate the medical literature, which is a lifetime task for all of us. I think when you're training, you must feel like this. You must be a clinical fellow if you're working in a more basic lab. So prior laboratory experience allows one to see physiological insights. My own experience with discussing the importance of transmural pressure at the bedside and the appreciation of the plateau of the cardiac function curve have been very helpful when I treat patients. Research for the practicing clinician validates what we know, maintains intellectual honesty. You don't have to run a study or initiate it, but you have to be willing to take part. And I think that is a moral obligation for physicians, and I would not hire anybody in my unit unless they were willing to take part in studies. I think you all have to be able to do that. You don't have to run it, but you should be willing to take part. You want to validate what we know. There are no absolutes, quoting Karl Marx on this one. All that is solid melts into the air. And think how things are always changing. Tight sugar, activated protein C, the strong allegiance to the ABC, airway, breathing, circulation, heavy sedation. These things are all changing during our careers. Getting tight on time, so we're going to skip some of these. We'll just use this example. So my own research experience being personal, I did a lot of work way back on nitric oxide synthase. And from the studies I did, I studied pigs and not rats or mice. And pigs have a very little amount of iNOS, the inducible form of nitric oxide synthase. And so do humans. So from basic principles and the experiments I did, I never would have taken part in the NOS synthase inhibitor trials because I would have concluded, I did conclude actually at the time, that it's not going to work. And they didn't work. The same thing with reactive oxygen species. I did a lot of work with these as well. And we also showed that there were signaling molecules. And so my thought was you have to modulate and not obliterate. And it's very naive to think you can come in and use these and affect ARDS or reperfusion injury. It's just a naive concept in how they work. So having had that experience and working with them in the lab gives you a very different perspective. Now, it doesn't mean a lot of scientists were also naive in how they used it as well. Again, we're just going to skip this because I'm getting a little late here. So limits of the scientific side. One of the things I like is physiology predicts nothing but explains everything. I was looking for the source of this quote, and I went to a site to find it. And what I found to my surprise, it actually listed me as the source. But I know I got it from somebody else, and I could not find the original source. But they referenced me. So research career, not for everyone. You have to be a little bit crazy. All of you are here for this. It's a major commitment in time. It's not funded like clinical work. You're exposed to constant criticism from granting agencies and journal reviewers trying to get your thing published. And clinical management can provide much more immediate gratification, at least when successful. But when not, actually escaping from the clinical side and going back and playing in the lab can actually be rewarding too. And I must say my own career, I feel like I'm going back and forth between them. At one point, get beaten up by the patients, great, you go back to the lab. Get beaten up by the journals, okay, great, I can go try to do something useful at the bedside. However, if you're crazy enough to do it, it can be extremely stimulating. It helps, I think, avoid burnout. I love what I do. I can't believe I get paid to do what I do, and I would never trade my career for anything else. It makes you feel much more intellectually credible. When I get up and talk about something on the science side, having done some studies, I just feel I can talk about it. Keeps you more intellectually rigorous with a healthy mixture of skepticism and optimism. And you develop international and national colleagues, which is a very special part of what we do. The reverse side, clinical experience for the scientists. Well, when the specific basic science information is provided to medical students, they can actually work things out at a much better way. I'm going to skip this one for the sake of time. And the key point, though, is you get constant feedback from your patient's experience. The ICU ends up acting as a living laboratory. And I think it's especially important for critical care physicians because I often used to say that our patients are better instrumented than my animals were. You get to test the generalizability of hypotheses. There's important cross-fertilization between fields. For example, cardiovascular, respiratory, and renal, because we just see them all the time. And the scientist at the bedside is key for that translational component of new knowledge. It can act as the translator between the basic scientist and the clinician. So the clinician scientist needs to maintain science experience as the clinician needs to maintain clinical experience. With today's rapid advances in science and clinical knowledge, this is not easy. You're going to get all this stuff on endpoints and that, so I don't need to do that. I just want to finish with this. Will the clinical science be able to survive? This is looking kind of scary, actually. A fragile link in the medical research chain going from discovery, translation, clinical trials to implementation. Here's some data from the U.S. Patient care, numbers of patient care physicians going steadily up, researchers staying the same and beginning to drop, teaching increasing. So with a huge increase in the total number, the fraction that are actually doing research going down. Or if we're looking at funding from the NIH, PhDs steadily up, MD PhDs really not doing much better than straight MDs in the US. And so this is a huge issue, is for the clinician scientists to get money to actually continue to do basic stuff. And we're actually getting squeezed out of that. And that's a huge problem in the North American scene. So in conclusion, the complexity of modern science as well as clinical medicine has separated these two domains so that it's difficult to do both. It really has becoming increasingly more difficult. The clinician scientist is an endangered species. Maybe we have to apply to the UN and get special status. Harder for the clinician to get funded for basic and innovative ideas, and difficult to compete with the full-time professional researcher. Even on the epidemiological level now, it's really becoming tough because of the training and the time that's involved. And yet, the bedside clinician is an essential link in providing validity to the system. Thank you.